Sum of two non-independent random variables. How do you handle that kind of thing? Okay, well, we're going to do an artificial example, no applications here. I hope I can think of an application for Thursday's class, though we probably won't go through the calculation details. There's a joint density for a bivariate random variable, a random vector, if you will, random point. They have joint densities. This is going back to chapter 5 again. You should not assume, in fact, if you're just sort of writing down some sort of joint density or at random, in all likelihood, the variables will not be independent. Because what's the definition of independence? It's that the joint density has to be the product of the marginal densities. In all likelihood, it will not be. Can we confirm that? Mm-hmm. Let's definitely have Mathematica help us with lots of calculations now. But you're going to need to pay attention to the key ideas, and I will write some things down as we go to remind you. So here I went ahead and put this function into Mathematica, and I went ahead and put it in as a piecewise function. One thing that would be good to do here is to draw this domain. The domain where the joint PDF is non-negative, is strictly positive, I should say, is when x is between 0 and 2 and y is between 0 and not a constant, but a function of x. A linear function of x with a negative slope. This domain is going to be a triangle. Let's draw it. So x goes between 0 and 2, and y goes between 0 and it was 1 minus x over 2. You will want to make drawings here with me in your notes. One minus x over 2 has a graph that is a straight line with a y-intercept of 1 and a slope of negative 1/2. Its x-intercept is 2. There's our triangle. That line has this equation. These inequalities mean we're inside this triangle. That is the domain in the xy plane where the joint PDF of this bivariate random variable is strictly positive. It's 0 elsewhere. Again, I did put it into Mathematica as a piecewise function just to see if it would work. The double ampersand here is to say I want both of these conditions to be true. Effectively, this is like an and. You put true here for the otherwise. That's just Mathematica's convention. And here I did want to confirm that the double integral of this entire thing over the entire plane, in fact, does integrate to 1. It is keeping track of the fact that it's 0 elsewhere. Takes a while to compute, but it does confirm it to be 1. But I also could do the double integral, not from minus infinity to infinity, but over the triangle itself, and it also confirms to equal 1. Okay, you want to write this PDF down if you haven't yet. It's going to be our example here. What am I about to do? I'm going to try to figure out once again the distribution of the sum x plus y. That's my goal. And I also want to confirm that it seems correct with simulations and that kind of thing. That's big picture where we're going here. Because the variables are non-independent, the CDF method still works, but it's just harder, you might say. Yeah, it is harder. We're not going to be able to use the convolution formula because that only works when the variables are independent. We're not going to be able to use the fact that the joint density is the product of the marginal densities because it's not true. First thing we should do is confirm that the joint density is truly not the product of the marginal densities. How do we do that? Let's find the marginal densities. What's the marginal density of X, for example? That is in the book, the definition of the marginal density. You need to integrate the joint density with respect to Y. You need to get rid of the Y, so to speak. What's the domain of the integral? It would be the values of Y that Y varies over for any given fixed value of X. Now I could go ahead and put all Y here. I could put a minus infinity to infinity, and that doesn't hurt. I will go ahead and put a minus infinity to infinity at the start. It doesn't hurt to put that. It's still true. However, for purposes of computation for this example, I want to imagine when doing this integral that X is fixed. And just like before, when I'm looking at the triangular region and imagine AX to be fixed, Y varies between the second coordinates of these points from 0 up to the second coordinate of that point, which depends on X. It's 1 minus X over 2. So this integral ends up being 0 to 1 minus X over 2. I'm integrating out the Y. What's left does depend on X. What does it equal? It's down here further. Where did I put it? Okay, it's this thing right here. Equals that. That's the marginal density of X. Let me go ahead and write down the paper. I'll write it with the X squared term first. Negative 5/8 X squared plus 7/6 X plus 1/6. What's the domain where this is valid? It's valid when X goes between 0 and 2. Right, in the triangle, X goes from 0 to 2. You might want to confirm that it is truly a PDF. We will do that. Just give us a minute here. How about the marginal density of Y? I do the analogous thing. I integrate the joint PDF with respect to X. If I want to simplify that domain to some finite domain, then I need to look up at my picture and think of Y as fixed, not X. And say X varies from the first coordinate of this point to the first coordinate of that point, not the second coordinates. 0 is the first coordinate. What's the first coordinate of that point right there? It depends on Y, not X. Take this equation and solve for X. X over 2 is 1 minus Y. X is 2 minus 2Y. That's the upper limit of the integral, 2 minus 2Y. Again, we'll have Mathematica do the details. What do you end up getting? Actually, I did them both here. You get this thing, 2y squared minus 14/3 y plus 8/3. 2y squared plus 14/3 y. Was it minus 8/3? Minus 14/3. Minus 14/3 plus 8/3. Yep, okay. I suppose part of your homework, I could just ask you to confirm this kind of stuff by hand too. I'm not exactly sure what the homework's going to be yet. This is a y going between 0 and 1. Think about the picture. Are these really PDFs? And can I visualize all these things in any nice ways? Yeah. Actually, let's go back up to the joint PDF. Here's another way to confirm that the joint PDF integrates to 1. Notice the difference between this double integral and this double integral. In this one, y is done first and then x. X goes from 0 to 2. Y goes from 0 to 1 minus x over 2. That's the way we've usually done it. But in this one, x is integrated with respect to first and then y. I switched around the dy and the dx. I therefore have to change the limits of integration appropriately. Y goes from 0 to 1. Look at the picture. Y goes from 0 to 1. And for any fixed y between 0 and 1, for the inner integral, x goes from 0 up to, there it is, 2 minus 2y. This should integrate to 1 as well. And it does. This can be interpreted geometrically. This graph, this red graph, is the graph of the joint PDF. Instead of the area under the graph being 1, it's the volume under the graph that equals 1. So the volume of the region under this triangular kind of graph here is 1. Ignore this thing over here, that's numerical error. It's not part of the graph. That volume of that solid would be 1. You can also interpret this in terms of what's called a contour map. This is the triangle where the joint PDF is positive, and you see level curves, which are straight lines because the joint PDF is a linear function. And I don't know if you can see those numbers, kind of small, but they keep getting bigger as I move to the right, which the graph keeps getting higher. The outputs of the joint PDF keep getting higher. What's the intuition beyond what this is modeling? This is modeling two-dimensional data, XY data, where X and Y have to vary over a triangle like this, and where the joint PDF is higher in value, the data is denser. We're going to ultimately see that by the end of the class here when I do a simulation. We're going to see denser data over here because that's where the joint PDF is higher in value, and less dense over here where the joint PDF is lower in value. Yeah, here are the marginal PDFs. Let's confirm these integrate to 1. Yep. So this first one, I'm integrating the marginal PDF of X from 0 to 2. And this one, I'm integrating the marginal PDF of Y from 0 to 1. I get 1 in both cases because I have to. There's the marginal PDF of X. There's the marginal PDF of Y. X, it's interesting. X has kind of a close to symmetric distribution between 0 and 2. And the data for X would be densest near 1. Y is kind of like an exponential decay. It's not an exponential decay, it's a quadratic, but similar in nature, right skewed distribution. The data for Y would be densest near 0. You might wonder if is that inconsistent with what we're seeing up there? That's maybe a little unclear. I think it is, with Y being denser near 0 is corresponding to the fact that these points have a Y coordinate near 0. Yeah, it's making sense. Here's something new. I've never shown this to you before. You can use a built-in command called probability distribution to create user-defined probability distributions, PDFs and CDFs. That's the marginal density of X. This is the marginal density of Y over the appropriate domains. This code doesn't really do anything seemingly when I enter it, but it did, and it stored some information in its Mathematicus memory. By the way, you might be wondering, where did I get this curvy D? if you do escape, SCD, escape, it makes a cursive D. SC, escape, SC, escape. You can just copy and paste it if you want. Seemingly it didn't do anything, but it did. If I now combine random variate with one of these things, that will simulate sampling from this distribution. So for X, this in all likelihood is going to be a number near 1 most of the time. Most of the time it's relatively close to 1 because X has a distribution whose mode is near 1. If I do it for Y, Y is right skewed, denser values near 0. In all likelihood, this is going to be a number closer to 0 than it is to 1 most of the time. I've never shown you that before. Probability distribution done in this way, combined with random variable, will simulate from these kinds of distributions, and I can do more than one sample. And here I'm doing 10,000 samples of size 1,000 and then making histograms as well. Hey, yeah, kind of looks like the shapes of those PDFs. What's the means? The mean of X is 17/18. I can that's confirmed with an integral. I can also confirm 17/18 with that simulated distribution. 17/18 there again. This is the standard deviation of X. Here's the mean of Y, 5/18, and its standard deviation, and those approximate to these numbers. Okay, now what am I after? Remember, so that's just all set up. Joint distribution of a bivariate random variable X and Y. Compute the marginal densities. Simulate the marginal densities if I like. But now the key, I'm after the key thing here. W is X plus Y. What's the distribution of W? Although I forgot to mention, it's definitely not, they're definitely not independent. Okay, these marginal distributions, if you multiply these things, you definitely do not get the joint PDF. The joint PDF is linear, whereas these marginal PDFs are quadratic, for one thing. That's true, so they're not independent. So again, I can't use convolution, I can't use independence in any way because they're not independent. But I can still use the CDF method. And I can still compute it ultimately by doing double integrals. The details are unpleasant, but doable. We have to split into two cases, though. That's an extra complication. Case 1, W is between 0 and 1. Case 2, W is between 1 and 2. Why? Why do I have to do two cases? Let's look at the picture again. Let me, in fact, redraw this. W is between 0 and 1. Here's the domain where the joint PDF is positive. However, the domain of integration to figure out the CDF of W is not the entire triangle. The CDF of W is where X plus Y is less than or equal to W. That's completely analogous to the other examples from today and before spring break. The triangle to integrate over is one like this, just like earlier today. If W is between 0 and 1. So I'm not integrating over the entire domain where the joint PDF is positive. I'm integrating over a smaller domain, a different triangle. And that line right there still is the same equation as before, Y equals W minus X. Because I'm thinking about where is X plus Y less than or equal to W. Equivalently, where is a capital Y less than or equal to W minus X? I'm using capital letters up there because I'm thinking of them as random variables, and here I'm using lowercase. Not a big deal. So integrate over that triangle is what we're doing here with case 1. So the limits of integration are what you see here. X is my outer integral. It goes from 0 to W. W, think of W as fixed. Some fixed number between 0 and 1. For any fixed value of X between 0 and W, Y goes from the second coordinate of this point to the second coordinate of that point, 0 to W minus X. That's the limits of integration for the inner integral of the joint PDF, which is this, and I cannot factor that as the product of the marginal PDFs. If I do, I'd get the wrong answer. Well, that's actually better here because the product of the marginal PDFs would be more complicated because they were quadratics. So it does actually make it easier to not do that here. Do the inner integral with respect to Y. So I need to integrate 4/3 X plus 1/3 Y with respect to Y first. I'll get 4/3 XY, because 4/3 X is like a constant, plus 1/6 Y squared. Right? Integrate 1/3 Y, get 1/6 Y squared. Y goes from 0 to W minus X. So when you plug in 0, you get 0. When you plug in W minus X, you get this. And then you'd have to simplify that. It's, a little unpleasant, but you could do it in about a minute or so and get this. And then integrate that from 0 to W. And here's the final answer in simplified form. It's fairly simple. When W is between 0 and 1. W is between 1 and 2, it's not so simple. We'll come to that. Here I did had Mathematica confirm calculations for me. Like expanding this thing here to get this thing. And confirming the integral does give you, in the end, 5/18 W cubed. So case 1, it's not terrible. Case 2, when W is between 1 and 2, I definitely would not want to do without technology. I mean, I could, but it's just like, it would be a real big pain. Why? Because the picture for case 2 gets more complicated. That's why. This green triangle shifts upward, so to speak, gets bigger, and the region to integrate over gets more complicated. It's no longer a triangle. What is it? Another drawing. I'm not doing this very well. If W is bigger than 1, if it's a little bit bigger than 1, what does the new triangle look like? The triangle where X plus Y is less than or equal to W looks like this. That's W there. This is still W here. But that triangle is not the domain of integration. Well, you could call it the domain of integration. However, the joint PDF is 0 up there because you'd be outside of the black triangle. So to actually do the calculation, you effectively have to think about integrating over this region here, which is no longer a triangle. Though you can think of it as a trapezoid and a triangle combined. So the point is you have to integrate over this trapezoid and then add the integral over this triangle, which does complicate things, and in particular complicates things in the sense that you got to figure out what the coordinates of that point are in terms of W. The black line has equation y equals 1 minus x over 2. The red line has equation y equals w minus x. To figure out where those intersect, you got to set them equal to each other and solve for x. So W minus X equals 1 minus X over 2. I could subtract 1 from both sides and add X to both sides, and then I could multiply both sides by 2. X is 2W minus 2. That's the X coordinate of the point of intersection. That point is 2W minus 2. Does that make sense? And that will be less than W when W is less than 2, which it is. And the Y coordinate I could figure out by plugging this thing into, for example, there. The Y coordinate would be W minus X, which is W minus this thing. And that'll be 2 minus W when you simplify it. Actually, we don't really need the Y coordinate, but I can find it anyway. In the end, what happens is you have to do the sum of two integrals, these two integrals. And doing those would be a pain. Very easy to make a mistake. If I had to do it, yeah, I could do it. I don't know, it might take me 10 minutes, something like that, I guess. Notice with the first one, X is going from 0 to 2 minus 2W minus 2. And Y goes from 0 to 1 minus X over 2, which is the black line. And for the second one, X goes from 2W minus 2 up to 2. No, excuse me, up to W. I'm integrating over this triangle here. And Y goes from 0 up to W minus X, which is the equation of the red line. And Mathematica says that's the answer. So altogether, W has, the CDF of W has a piecewise formula. And there it is in all its glory. Somebody can remind me after class to share this with you. Put it on Moodle. You might wonder, and you might hope, is this continuous? Shouldn't it be continuous? These pieces have to match up at 0, 1, and 2. And they do. You can plug in numbers to confirm they match up. Or you can just graph it. It's a continuous function. Its derivative is the PDF. Technically speaking, it's not differentiable at 0, 1, or 2. There's corners in the graph, I think. Well, actually, it would be differentiable at 0. Probably not at 1 and 2, though. There's like corners. There's a corner in the graph for sure here. Maybe it kind of like at 1, it looks like maybe it's smooth there. Hard to say for sure. I just differentiated the pieces and didn't worry about the endpoint. So if you differentiate this thing with respect to W, bring down the 3, 15/18 is the same as 5/6 W squared. 5/6 W squared. Differentiate this one, you'll get negative 11/6 W squared plus 14/3 W minus 2, it looks like. Yep. This can be put in. This turns out to be continuous as well, though it didn't have to be. So I guess it does mean it's differentiable at 0, 1, and 2. I wasn't necessarily expecting it to be continuous. It does integrate to 1. What's its mean? It turns out to be 11/9, which is approximately 1.2. What's its standard deviation? Turns out to be about 0.37. Remember my goal. Now, okay, part of the goal has been met. I'm saying there's the PDF of W. I did double check it. In fact, this example was from a different book, and that was their answer too. So this is right. What I'd like to do now to finish class is try to confirm this simulation-wise. Like, Again, this is the main theme, confirm theory with simulation if you're feeling uncertain about the theory, which, you know, you very well may be. I wanted to confirm it with simulation. So I can do the probability distribution thing that I already showed you. I can make a histogram and plot it with a PDF and see that I got a good match. That's some confirmation. That's the PDF of W multiplied by 1,000 to make it scaled up. Matching the simulation, that's good. That's actually not really confirming that I haven't made a mistake though, because I'm just using my answer in both spots. There and there. The mean should be close to, what was it? 1.2, and the standard deviation should be close to 0.37. That's simulated data there. But here's the kicker. Can we do a simulation to confirm it's truly matching the behavior of the sum x plus y? Low on time here. Have to do a quick explanation. To get Mathematica, I was hoping I could avoid this in Mathematica, but it seemed that I couldn't avoid it. To get Mathematica to confirm this, I had to actually compute the conditional densities, or one conditional density at least, which we haven't talked about all semester. It's in chapter 5. It was in Prob Stats. It's related to curves of regression. And in fact, I'm going to show you a curve of regression here. The density of the random variable y given x equals x. In other words, if you know what value x takes on, what's the behavior of y? That's the definition of the conditional density. It equals this in this example, it turns out. When you look at this expression, you want to think of x as fixed and y as the variable. And if x is fixed, then that's a fixed right endpoint as well. This does integrate to 1, though it doesn't look like it will at first. When you integrate it at first without doing a simplify, it gives you this answer, which you're like, oh, that didn't integrate to 1. But if you simplify it, that's actually a big, crazy 1. The area under this graph is 1, no matter what x is. But the domain does change, and the graph itself does change. Those are the conditional densities for different values of x. What's the curve of regression? It's the mean of those densities. I'm integrating with respect to y times this conditional density. This thing depends on x, and you can't get rid of the x there. If you plot that function of x, you get this pretty picture showing you that for different values of x, I can approximate the mean of the corresponding value of y by this curve. This is the curve of regression. For example, when x is 1, I should expect the mean value of y to be close to 0.3. But how do you simulate that? That's all this stuff, and I'm not going to take time to explain it. But there we have simulated data for the joint distribution, matching the density, the joint densities being more dense down here and less dense over here. And this is finally where I'm taking that simulated data and adding the x and y coordinates essentially. And this is the final confirmation. This is close to 1.2 and this is close to 0.37. Without getting into details of fully explaining everything. So yeah, I'm not exactly sure what form your homework's going to take, but I will put this on Moodle. Somebody again remind me. And even though that was difficult, I hope it still felt rewarding to see everything come together.